Now let's proceed with the next topic, which is all about total differential using partial derivatives. This total differential, we've already solved for this when we had the total differential discussion for our midterm. Now, this is expressed in terms of dz, and then as you can see here, we have the curly z with respect to x times delta x, wherein the increment, if it is sufficiently small, we can actually express that in terms of partial derivatives times the differentiating variable, and then you can also do that to the rest of the multivariable functions. Now let's solve these two problems. So we have, for the first one, we have u is equal to 3s squared t plus 4t raised to negative v. What I'll be doing first is I'll be solving this for the total differential using our midterm. So in that case, this one becomes du, because you have to just like take the total differential of this one. So we have 3s squared, and that is actually product rule, so that's dt plus t times the derivative of 3s squared, so that's 6s, and then ds. Okay, so that is for our first term. And then for the second term, we know that this is some kind of u to the v. So we have 4 times t to the v. I'll be using the direct differentiation method. So we have negative v, and then t raised to negative v minus 1, and then the derivative of t is simply dt, and then we add t raised to negative v ln of the base of t, and then the derivative of v is negative dv. Okay, so with this, du, or the total differential, is equal to 3s squared dt plus 6st ds, and then we have, I think, negative 4v t raised to negative v minus 1 dt, and then we also have negative 4t raised to negative v ln of t, and then that's dv. Okay, and then if we try to combine all the like terms, so we combine all of those, we have dt, so we have 3s squared, and then minus 4v t raised to negative v minus 1, that's dt. And then for ds, we only have 1, so that's plus 6st ds. And then we finally have this dv. So we have minus 4t raised to negative v ln of t, and then dv. Okay, so as you can see here from our answer key, we already have obtained the correct answer. This should be something like small s. Okay, but and also this one should be small v. Okay, but the thing here is that this was solved using our midterm concept. So we'll be applying what we know in partial derivatives, that if we have u here, so we know that du, or the total differential, is simply the partial derivative of u with respect to x, and then times dx. You add the partial derivative of u. Actually, we don't have any x here, so we'll be using the rest of the variables. So we have partial derivative of u with respect to s, and then times ds, plus the partial derivative of u with respect to t, and then that's dt, and then the partial derivative of u with respect to v, and then dv. Okay, so with this, let's apply this to our expression. So we have du. I'll just be removing this because we've already proven that that's the correct answer using our total differential. So I think I'll be deleting this first. Oops. Okay, so that we're left with this expression, and then I'll be moving this at the top. Okay, so following all of this, we know that du, so we need to take the partial derivative of whole expression with respect to s. So if that's the case, then treating s as the variable and the rest as being constant, so we know that this is 6st, okay, and then for this one, we have only a constant here, so that will be ds. Okay, so that's it. We're done with the first term. Now for the second one, we need to treat this s and v being constant. So with this, we have plus, and then that will be 3s squared, and then t is simply dt, but we also have t here, so we proceed first. That is plus 4 times t raised to negative v, and we know that if t is a variable and negative v is a constant, so this is actually This is actually a power rule, so let's delete this one. So with this, we have 4 times negative v, and then t raised to negative v minus 1. Okay, so that is dt. So this whole expression here is actually equal to, this will be multiplied with dt, and that's actually equal to the this expression here. And then we have the last term. We need to take v as the independent variable here, the rest being constant. So we have 0 for this one. And then for this one, we know that the base is constant. So we have 4t raised to negative v, and that is simply taking the ln of t, but we need to differentiate v, so that's negative 1. So that's negative 1, and then we attach tv, because that's based on the expression. So with this, du is simply equal to 6st ds, and then I think we have plus 3s squared minus 4vt raised to negative v minus 1, and then that's dt. And then finally, we have negative 4t raised to negative v ln of t, and then that's dv. Okay, so I think we have already obtained the same answer from our key. And the good thing about here is that when you do partial differentiation, total differentiation using partial derivatives, what you'll be obtaining is something like the expression is already multiplied with all the remaining expression that has the differentiating variable on it. Because I remember the last time we did this using our total differential, as discussed on our midterm, we still have to modify or regroup the expression so that all the expressions with its corresponding differentiating variables are written on it. So in this case, 3s squared minus 4vt raised to negative v minus 1 is already on the inside, so like multiplied to dt, instead of having it regrouped from the solution using our midterm. So that's it for this number or example. So let's have the second one. We need to find du in this expression. So I'll be using the total differential using partial differentiation because that's our topic. So du is equal to, so this is with respect to x and z, x, y, and z. So for with respect to x first, I have 1. And then for this second expression, we have negative 2xy. So that will be dx. Okay. And then for the second one, I'll be doing y. So plus, that's 1 for y. And then we also have negative x squared. So that's dy. And then for the last one, I'll be doing that for z. So for this one, the derivative of z is simply 1. And then I think there's nothing more. So that's 1 times dz, so that will be dz. Okay, so I think this is our final expression. And let's counter check to that. So, okay, we obtain the same answer. So that's just how simple this total differential works in terms of partial differentiation. I think this is kind of easier, but of course, when you're more comfortable doing the process in our midterm, then that's just perfectly okay. Now let's have some more. And in this expression, as you can see, we don't have any expression as if it's written like, let's say for example, we have f is equal to this expression. This one is actually written as if it's xy is equal to the expression. So we're in, as you can see here, we have xy and then we also have xyz here. So it's like it's not written in a way that like this. Okay, and basically the problem here states, or the general expression here states, that we need to use this formula. But how do we do that in this expression? So what you can do right here is, if you're applying your midterm idea about total differential, that would just be implicitly differentiating this expression. And we can also do that in partial derivatives. So what you have to do is to treat this as if it's the u. You both have something like u on both sides. So with that, you just have to take the derivative of each of them with respect to x, and then just proceed with the regrouping at the end. So with this, I'll be doing this xy on the right side. So we have the derivative of this with respect to x would be simply y, and then that would be, of course, multiplied with dx. And then I'll be doing x for the right side, so you just have to write the equal sign, and then we have 1 over x plus y plus z. Okay, and then we have the derivative, which is actually 1. So we have plus e raised to negative xy z, and then the derivative of this one is actually negative yz, and then you attach dx here. Okay, but knowing that that's just dx, we have to proceed with the solution, so we need to add y in this case. So we have we need to differentiate this with respect to y, so we have x and then dy, and then of course we need to do that the same for this right side. So we have plus that's 1 over x plus y plus z again, and then we have plus e raised to negative xyz, and then we have negative xz. That's of course dy. Okay, and then for dz, we know that this one doesn't have any dz expression, so that would be just 0. And then for this one, we add 1 over x plus y plus z, and then we have plus e raised to negative xyz, and the derivative is negative xy. Okay, and then that is multiplied with dz. So with this, we can now try to regroup all of these expressions. So I think we'll be having something like, let's have this transposed to the right, and then let's just leave z at the, let's transpose this to the left, and then let's leave this expression at the right. And you can always follow what you want in this regrouping. It's just that I want that way, so it doesn't matter anyway. So this one can also be the final answer, but let's just have all the dx's in one term. So we have, I think what we'll be getting is y, and then minus 1 over x plus y plus z, and then this one being minus, but this one is negative, so that becomes positive. I think positive yz e raised to negative x y z, and that is multiplied with dx. Okay, and then the same thing goes for dy. So we have I think we have plus x minus 1 over x plus y plus z, and then we have minus plus xz, and that is e raised to negative xyz, and that is dy. Okay, and as what I've said before, I'll be leaving dz at the right, so I'll just have here 1 over x plus y plus z, and then minus xy e raised to negative xyz, and then that is dz. Okay, or you can always try to transpose z at the left and then equate this to 0. And I think let's just look at the final answer. So the final answer in your module is something like this one. So I think we have the same final answer right here. So at the left is the dx and the dy expression, and at the right is the dz expression. So you have plus here, and then this one is minus. Okay, so I think that's the same answer, exactly the same. So that's all for this example. Now let's proceed with another. Now this one is where our chemical engineering starts. Okay, so this is a part of physical chemistry subject and or thermodynamics concept. So we have the total differential of enthalpy for its path function, that is dH is equal to Cp dt. Now, just to give you an idea of what this means, dH is the change in enthalpy, and we know that enthalpy is the sum of the internal energy subtracted with the pressure volume work. So with this, we have the specific heat capacity, and we know that specific capacity is the capacity of an object to something like absorb heat and then change its temperature. So dt is the change in temperature. So this is given in a constant pressure, and we need to express this specific capacity in its partial derivative form. So this is the answer, partial derivative of h of partial t. Now, I want you to understand that this is read as the partial derivative of h with respect to t at constant p, that is equal to the specific capacity. So this one is read as at constant this variable. So with this, we need to find that expression. And do you know that it is very easy to do that when you have this general total differential given? So we have Cp dt. So what you have to do is to copy this expression at the left. Usually that's on the left. So if you want to express that, that will be partial h, of course, and then you just have to take the partial derivative of the differentiating variable at the right. So that will be divided by the partial derivative of t. And of course, since this problem is given at constant pressure, so based from the given, we could just add something like a bracket or parenthesis, and then at the bottom portion of that parenthesis, you add something like p to indicate that this process happened on constant pressure, and then that will be equal to what is left on the expression, so that's Cp. So it's like, imagine having this dH dividing it by dt, and that is equal to Cp, and then you you transform that in terms of partial derivative, of course, by having this constant pressure. So it's like what happened here in a more general and more, easier way to view this. So do you know that if you have dt, that is equal to dH over Cp based on this whole expression. So you can also express this in terms of the change in temperature with respect to the change in enthalpy at constant pressure. That would also be equal to 1 over Cp. But this is not a usual expression that we can see, because what we have here is the change in temperature, and we know that the change in temperature is actually more of the independent part of our example, or the more independent variable in our real world. So because this delta H, what you can see at the numerator of any partial derivative is usually the dependent variable, and the one that is at the bottom is usually the independent variable. So with this, if you try to interchange that, although that is mathematically correct, the expression here doesn't look practically correct, because the enthalpy is not really that independent. It depends upon the temperature, so it's the other way around. So mathematically you can do this, but in the real setting this is not kind of allowed. So I'll just be removing that. I just want to show you how this interchanging works. But then again, you just have to look at this expression at the left, and then just know the independent and dependent variable in that case, and then the dependent variable should come at the numerator, and then the denominator being the independent variable. Okay, so that's just how simple this problem works. And then for the next one, we have this expression, and then we need to, it's the other way around. We need to provide a total differential. So with this, coming from this idea that we have the partial of u with respect to T, temperature, and then at constant volume, and then we have the specific heat capacity at constant volume. So this CV is the specific heat capacity at constant pressure. Now, you might be noticing that in your chemistry, you're just using Cp. So that is actually a specific heat capacity at constant pressure. Now, if you have specific heat capacity at constant volume, that Cp changes into Cv. So anyway, so what we have here is this expression, and then based on our expression, we know that this is the dependent variable. So it goes to the left, so that's du. Instead of having partial or curly d, we have d, and then that is equal to Cv. You just copy this one and then dt. So that's it for our final answer. And then this v, the constant volume, you don't have to indicate that in your expression. It's just that it's the condition that's happening, something like at the background of this expression that we have. And now for the last one, what we have is the expression of the internal energy. I know you're quite bombarded with this internal energy, this enthalpy, entropy, even though you don't have enough discussion for that. But I'm telling you, you will be getting a lot of this when you have your thermodynamics, physical chemistry, and when you don't have enough idea or knowledge about partial differentiation and total differentials before you start doing thermodynamics, that will be a lot difficult when you can't even read this kind of expression. That's why I'm trying to give you these discussions. Although this discussion is no longer included in your syllabus. I mean, the CMO dropped down by the CHED. It has all the topics that we need to discuss, but these ones are actually additional topics that I have included because I think this is very essential in learning chemistry and learning differential calculus before you start thermodynamics. So with this, we have this expression, and we need to provide the complete expression for the partial derivative of the internal energy. So this is the expression for the partial derivative of internal energy. So what we do here is we start with the original expression. We have dq plus dw, and then we try to substitute this with the expression. So we have du, that is equal to tds, and then minus pdv. And by the way, this is the general expression of our internal energy. This is the first one, but this is the second general expression. In terms of the temperature, the entropy, and this change in volume. This one is the pressure. So, applying the same concept on what we had before, because what we did here is simply, we have dh and the cpdt. We only have two variables that are actually changing here. We have the h and then the t. But how about this one? We have actually two of them. Okay, so with this, what we have to do is to set the changing variable as constant in this case. So we have du. The first one is that we deal with this first expression, and then imagine if you don't have this expression yet. So what you'll be doing is something like, to express this expression, what you'll be getting is partial u over partial s at constant, whatever it is. I don't know why, but that will be equal to t. It's something like that. So if we do that on our expression here, that's the same thing. So that's partial of u, so that's our dependent variable, and then the first independent variable, that is our entropy. But what is the constant in this expression? Again, you have actually two differentiating variable that you have here, that's s and then v. So if you want to get this kind of expression, all you need to do is to set the remaining differentiating variable as constant. So with this, we don't have to look back at our problem, because you can see right from here that we need to set this as constant, so that becomes constant v. Okay, and then of course, based on our total differential, you have to add ds at this expression, because that's what happens when we try to do total differentiation. So you might be wondering why I didn't do something like that in the previous example, because that's basically having this expression only without any dt. That is true because we only have two variables here that were concerned, the dependent and the independent variables. So we don't have to attach another infinitesimal change in our partial derivative. But with this, we know that we have three variables, and then two of them independent, changing at a time. So we need to attach another incremental variable right here. And then we do the same thing for this one. So we have minus, and then we take the partial derivative of u, and then by virtue of this idea, so we complement this idea, so we have partial derivative of v, and then so you might be thinking that we need to set another constant here, so that is at constant entropy. So it's like interchanging them, and then of course you have to attach dv in this case. Okay, so with this, you have arrived to the final expression for your internal energy. And again, from this expression, do you know that this whole term, if you try to match the expression above this one and then this one, can you see the similarity wherein you have ds here, ds, du, and then dv. So therefore, if I want to match these two expression right here, you can see it from this expression, this t, and then the one corresponding to this partial u over partial s at constant v should be equal. So in this case, we know that we have partial u and then partial s. Let's use another color. This is not included in the problem, but we can just generalize that the partial u or partial s, the change in that at constant volume will always be the temperature. And then for this one, we have the change in internal energy with respect to the partial change in volume, that is the entropy, that is equal to our negative pressure. Because that makes sense when we try to remove this, and then I show you how this works if it's partial u and then partial s with constant volume. That will be t in this case. So that's the same thing as what you can deduce from this expression, but it's not asked in the problem, but I want to show you that this is the equivalent. So if you're asked, for example, what is the change in internal energy with respect to the entropy at constant volume. So you know that that is actually the temperature. Or if you've been asked what is the change in internal energy with respect to the volume at constant entropy, so you know that that is actually the pressure of the negative pressure of the system. Okay, so that's it for our Clairaut's theorem.